about piecewise circular curves and flag positivity. So this is kind of a toy project I had with a collaborator, Ryan Kirk, who's at East Carolina University. East Carolina doesn't exist, but East Carolina University does. It's in North Carolina. So the motivation for this project is to sort of build a new toy model for higher Teichmüller theory. So I will say what that is and why we might care. But most of the math that will be in the talk will be fairly elementary. And it might be interesting to some of you, because I know there's a big like symplectic and contact geometry group here. This is my first time writing the words contact form in a paper. So I'm definitely not a specialist, but I'm interested in learning more. So if this piques your curiosity, I will want maybe to speak with you afterwards. So this is an example of the type of object that I'm going to talk about later. So it's a piecewise circular curve. So you can see that it's a curve made out of pieces that are arcs of circles. And then there is a choice of normal direction at each point.
So where is this curve living?
In the sphere, in the two sphere, yes. So you can imagine that when it goes out to infinity, it's coming back afterwards, inverted. So this is actually like a loop of motions of this curve in the sphere. And then I have another example of a curve here. I will tell you what the difference between those two is. Both of them are a little bit special in that when I apply this sequence of moves, or this path of moves, they never self-intersect, even in this in the picture that I'm drawing. So I'm always moving in the normal direction that I've chosen in a continuous way. And this curve stays a simple curve in its projection to the sphere all the way.
So that's a
way through this path.
That's a requirement, or just happens in these?
It happens in these cases, yeah.
So in
general, what I call a piecewise circular curve can have self-intersections.
Yeah.
Okay. So and then there's a third picture that I wanted to show. This has more pieces. This has 20 pieces of circular arcs. And I'm not sure if I'll show them again, but I wanted to give an idea of what they look like, and they're difficult to draw on the board. And the rest of the talk will be on the board, so that's why I wanted to show pictures at the beginning. Okay, so now I can turn this off, unplug this, and do that, and this thing. Okay. And start to talk proper. Okay, so I'm going to tell you a little bit more formally what a piecewise circular curve is at first. Then I'm going to tell you about Lie sphere geometry, which was in my description of this talk in my abstract. Like I said in the abstract, it's something that was invented by Sophus Lie, the same Lie as Lie group, but has been completely forgotten, or at least mostly completely forgotten. I had never heard about this before I worked on this project. I sort of found out about it by mistake, by coincidence. And then I'm going to tell you the second part of this title, so the positivity. And then depending on what time is left, I will tell you more things. So these are things that I want to do. And we'll see later if I have time to say more. Okay. So, so the first part, what's a piecewise circular curve? So you, it's what you expect. So it's a curve in S2 made of circular arcs, so piecewise circular arcs, such that the tangent lines at the vertices agree. As in the animations and pictures that I showed before, I allow the tangent lines to agree even if the curve is not smooth. So like something like this is allowed. So they have the same tangent line, even though there's a singularity there. Now, in order to deal with these a little bit better, the curves that I will be talking about will also have a choice of, like I said, normal direction at each point. There's different ways to talk about this. So a co-orientation on such a curve. Oh, and so this one is an example of a closed one. All the ones that I will consider in the talk will be closed. So a co-orientation is a choice of a continuous choice of normal vector at each point.
But like at the cusps,
Yes.
you have to say something else.
At cusps, no, it has to be continuous. So if you choose here, this normal vector, at this point you have this one, and you have to continue with this one on that piece. Otherwise, it wouldn't be continuous. So you don't switch; you keep the same one. So it's a continuous lift to the unit tangent bundle if you want, or maybe slightly more naturally to the spherical cotangent bundle of like contact elements, oriented contact elements, depending on how fancy you want to get with the definitions. But these are all the same because this is very elementary. Yeah, so this one, for instance, cannot be oriented, so it's a bad example, because I'll end up with a contradiction if I come back here in my continuous choice. So this cannot be co-oriented as a closed piecewise circular curve, because I have one of these singularities which switches the direction, like switches the direction on this circle from pointing outside to pointing inside, and then it never reverses again. So if I had two singularities, then I would be fine, or zero. Yeah. Now, I don't want to write closed co-oriented piecewise circular curve with k circular segments a bunch of times, so I'll give a name to this. So circular polygon is a closed piecewise circular curve with a co-orientation. Now, I'm interested in a sort of classification theorem for these. So what can we say about the moduli space of these things? Now, in order to make that question formal, I should define the moduli space for these things. And for that, I need to choose what will be my equivalence relation on piecewise, on circular polygons, right? So you could, for instance, ask what is the moduli space of all circular polygons up to isometry of the sphere? But that's not what I'm interested in. I'm trying to put the largest, the least restrictive or largest equivalence relation possible on these things that makes sense. But I don't want to go all the way down to just like homotopy or something. So what is a natural equivalence relation to put on these things? Well, so first, you can apply a Mobius transformation to a circular polygon. And because Mobius transformations preserve circles, okay, they might send them to a line. So because you want this as your part of your equivalence relation, you also have to allow straight pieces, which are just infinite radius circles if you're drawing them in the plane. But since I said in S2, well, a circle in S2 includes lines if you're doing the stereographic projection. Okay, so you can apply Mobius transformations to one of these, and it stays one of these, stays in the same class. But there's also another thing you can do, which is what I had in my animations before, which I'm not completely sure how to call. In the paper, we call them equidistant transformations, or like radial translations, something like this. And all of these are contactomorphisms on the unit tangent bundle with the expected contact distribution. So what is this? This is just translating or growing each circle. And that's in a Euclidean sense by a fixed amount. And it's a signed amount. This is not super formal, but I will make this a lot more formal later when I tell you what this moduli space really ends up being. But I want to convince you that it's like a natural question just from this elementary point of view. Like if you apply a sequence of these two moves, any Mobius transformation you want, or this other type of transformation, which it's interesting to see what it does if you have this type of piece on your curve. So when I say growing by a fixed signed amount, it means going in the direction of the normal direction that I chose. So if I apply one of these transformations to these circles, they have centers in the plane, and they have a fixed radius. Say I increase the radius by 1, then this one, I will think that it has a negative radius because it's pointing inwards, and this one has a positive radius because it's pointing outward. So it will grow the one on the right, but shrink the one on the left, and so they stay tangent at the place where they intersect. No? And if I keep going, eventually this one will shrink to a point and reverse. And I'll end up with something like this.
Say sort of circular curve. What do you mean? Where are you working? Because you seem to be mixing geometric models here, and I'm confused because you have Mobius transformations.
Yes.
And all sorts. So you're thinking of S2 here as sort of like a fixing something like a conformal structure or something as CP1 or what?
I will clarify this also a little bit later. So yes, I'm thinking of CP1 with fixed conformal structure, but I'm working really in the unit tangent bundle of CP1. Otherwise, this wouldn't make sense. I couldn't, for example, like shrink a circle to a point and then open it back up in the different direction. But if I'm in the unit tangent bundle, then this makes sense because I'm keeping track of the directions. So like, I want to consider this also as a circular arc with a circle of radius 0. Does that answer your question?
Yes, and for a metric you're using.
Yes, I'm not using a metric.
Okay.
So circles make sense even without a metric. When I say these equidistant transformations, this is because I'm trying to give you like a simple way of generating the equivalence. So it's generated by these two things, where for doing this one, you can pick any affine chart, any the Euclidean metric on that one, and this will be in it. And any other choice of chart with its Euclidean metric will also give you a transformation, which is in the equivalence relation that I'm trying to generate.
What if you do a one parameter family of Mobius transformations?
Yes.
Well, so that's a different picture than this the second equidistant, right? I mean, I'm just wondering what's happening. Is that a clear question?
I
I mean, just imagining you're doing a deformation of,
Yes.
of your circular curve. Now in here, which isn't paying attention. Well, I don't know what's going on. I guess I'm asking, what is the picture of a one parameter family of Mobius transformations
acting on one of these.
acting on one of those? Yeah.
It will be exactly the same as if I didn't pick a normal direction. So you just act on the circle, on the circular arcs. Like you act on the points of CP1, the same way the Mobius transformation would, and it will deform the piecewise circular curve. So, okay. These are different types of transformations in the equivalence relation that I'm building, because this one acts on the points of CP1, whereas this one does not act on the points of CP1, it acts on tangent vectors to CP1.
Yeah.
So it might blow up a point to a circle with normal directions, but its action on the unit tangent bundle is well defined. I'm going to make this better. I'm sorry for the rough beginning, but it will make sense, I promise.
Again, to define the unit tangent bundle, you use a Euclidean metric.
You can do the spherical tangent bundle if you want.
You can use the standard metric on S2.
You can, but I think it's more natural to not choose a metric. So circles make sense even in just Mobius geometry.
Yeah, but for the unit, to say the vector is of unit length, you need a metric.
Or you can do the projectivize, like mod out the tangent bundle by positive multiplication. You mean to say that it's normal to the circle? Right.
Well, that it's fine because they all conformal.
Mhm.
But I mean, for the length, no, you say it's
To
unit.
define this transformation, you need to choose a length, yes. But when you take the set of all transformations of the unit tangent bundle generated by these two, it ends up being just the symplectic group, actually. So that's what I'm going to say, but you're making me get ahead of myself. This will make sense. Okay, so this is the sort of baby picture where we can draw these pieces of circles and play around with them. And now we want to say, what's the collection of all these circular polygons up to these two things? So I'm allowed to apply any Mobius transformation or a sequence of these moves in any affine chart for CP1. So the first invariant that's sort of obvious in this is, so as curves in the unit tangent bundle of CP1, so this is the unit tangent bundle of S2. So if RP3 has a topological manifold, they have a homotopy class. So that's maybe the first invariant you would think of. A circular polygon is either contractible or not contractible, right? In one of two homotopy classes. As loops say. So you already split your moduli space of piecewise circular curves or circular polygons into connected components. Like there's a collection of connected components, which is all the contractible loops, and another collection, which is all the non-contractible loops. That's sort of the first obvious thing you notice about these objects. Now, if you want to say something more, the problem is that when you rigorously define this moduli space, it's not a manifold everywhere because there are certain more degenerate configurations. So you want to look at generic circular polygons. There's some things you don't want to allow. So generic, or a circular polygon is generic if it satisfies the following two things. So first, two non-adjacent vertices are not tangent to a common circle. And whenever I say the word tangent, I will mean tangent with the orientation matching with what the tangent is. So these two circles are tangent, but if I flip the orientation on one of them, even though they're geometrically tangent, I won't call them tangent because the normal vectors don't match. And they would stop being tangent after applying one of these transformations. So that's why it doesn't make sense to call them tangent if they're both pointing outward and they're outward tangent. So what does a curve which violates this look like? Maybe you have like you start drawing your co-oriented piecewise circular curve, and then if I have this as a vertex and this as a vertex, that's a problem because there's a circle which is tangent to both. So it won't be a problem if I pick this edge as my next edge because I said non-adjacent. And anyway, for sure, adjacent vertices are always tangent to a common circle because that's in the definition. But non-adjacent, I don't want them to be part of a common circle. So like if my curve continues over there and then does something, I don't know, and then continues over there, this is not allowed. Orange is good for not allowed. And then second is sort of the dual statement of this. So two non-adjacent edges are not pieces of tangent circles. So how would I do something which violates this one? That's fairly easy. So if I draw two tangent circles, then I don't want to have like an arc of this one somewhere in my curve and an arc of that one somewhere in my curve. They should be tangent. So if this one points outward, this one has to point inward. So I don't want to have a curve which is where these are. I don't know what happens in the rest, but I don't want this to happen. So, yes,
I'm imagining that the only way to sort of flip orientation is going through cusps. I'm trying to
what do you
read.
mean? If you're continuously moving in this space,
Yeah.
yes. So the orientation If you apply only Mobius transformations, you will never invert.
Yeah, I mean, I guess what I'm asking is I'm trying to look at one and wondering, is there a more combinatorial that between any two non-adjacent vertices, there has to be like a cusp or I don't know.
I mean, so there are more combinatorial figs which imply this, but I don't know how to say exactly this in a combinatorial way.
Okay.
Right. Now, okay, another property of these curves, which is fairly easy to define, is them being simple. So I will say that a circular polygon is simple if every representative of the equivalence class is simple. So it's pretty easy to find examples where it might be simple in one, like depending on how you draw it, maybe like this. Like this one is smooth, so it is simple if you draw it like this. But then if you apply some of these equidistant transformations, eventually this circle will shrink, and this will turn into something like, no, like this. And so this is not simple. But the animations that I showed at the beginning are examples of simple circular polygons. I did not, like, the animation doesn't prove that they are, but the animation together with the statement that I guess these generate the whole equivalence relation should be enough, because clearly these do not introduce self-intersections, Mobius transformations, because they send points to points. But these might, like in this case.
So sample is that there's no intersection, so no self-intersection.
Yeah.
The equivalence class.
Yeah, no self-intersections. Yeah, simple, right. I should probably not use simple in the definition of simple. Thank you. Has no self-intersections. Or at least the points don't have self-intersection. Here, I guess the tangent vectors don't intersect, but I still call it a self-intersection. Yeah. I screwed myself. The order of the boards is always a problem. And then there's another property which is a little bit harder to define, but I will mention it later. So the theorem that we prove in the paper is that in the moduli space of circular 2k gons with k at least 2, the connected component, or the subset of simple and decreasing curvature, which is the thing that I will define later. Polygons is a connected component. Homeomorphic to a ball. Generic. Okay, so the dimension of this, okay, so this, if you use the word generic, this is to make this moduli space a manifold. I will explain why it's a manifold. And the dimension is 4k minus 10. I'll also be able to tell you why that is. So there is a very special subset of generic circular 2k gons, which satisfy this property. So they never self-intersect in the whole orbit under these equivalences. And they have this other property, which essentially says that, okay, so curvature for a circle is inverse of radius. So decreasing curvature should mean that when you move around the curve, the radius is always growing. But that doesn't make much sense because we're on the sphere, so you can't grow forever if it's going to close up. But there's a way to assign a cyclic order to the radii of the circles, and then you can tell whenever you have 3 circles if they are nested or not, and you want all of them to be nested whenever that's possible. So I will explain what that is in other terms, so that I can make this theorem statement a little bit more formal. Okay, so now I will reveal everything that is.
So you equal to 2, the dimension is negative?
I mean, it's a bunch of points when k is equal to 2. So it should be 0, yeah. So for the dimension to be right, k has to be at least 3.
Okay.
But when k is 2, the theorem is still true. It's just that the dimension is 0. Yeah, there's no negative dimension, you're right. If I remember, there's either 2 or 4 points in the moduli space if you're doing k equals 2. I don't remember. I think I've written it somewhere, but okay. Let's go to the second part where I can reveal everything. Okay, so this was created by Sophus Lee, as I said. Invented in the 1870s. Apparently, at least according to historical texts that I found, he was very proud of discovering this geometry. And like I said, everybody forgot about it. So it's as an analog of projective space. Where instead of considering lines as points, you consider your circles as your points. So in a sort of axiomatic way, right? So instead of lines being points, circles are points. And the important geometric feature, the incidence relation, so in projective geometry, in projective plane geometry, 2 lines are incident if they intersect, and incidence is given by intersection of lines or collinearity of points. Here, incidence of circles is tangency. The sphere transformations are tangency preserving transformations. So in modern language, what this is a homogeneous space of the group O(n+1, 2). So it's the space of isotropic lines for the natural action of this on Rn+3 with inner product of signature n+1, 2. But I'm interested in circles, not spheres, so I care about n=2. So for n=2, this is O32, and you have another, you have an accidental low-dimensional isomorphism of Lie groups, which tells you that there's a local isomorphism between this and the symplectic group. And the 4-dimensional symplectic group. So the space of this Lie circle geometry, the space of all circles, so will be circles in the sphere with an orientation, has an action of this group, which is 10-dimensional. And this is related to the 10 up there.
Local isomorphism, you say it's the
The
algebra.
algebras, yeah. Up to choosing connected components and maybe quotienting by something, these are isomorphic. So, there's a way, and I like to, at least in 2 dimensions, I like to describe this homogeneous space in terms of this group instead of this one, because it makes the contact geometry a little bit easier. This acts on RP3, preserving a contact structure, and this is where all this business comes from. So which homogeneous space is it? So the Lie circle geometry is so the 2-dimensional version is essentially the geometry of the Lagrangian Grassmannian for this group. So in R4. So that's the homogeneous space, and the transformations are SP4R transformations. How do you get a circle from a Lagrangian subspace in R4? So here's the trick. Consider C2 as your real vector space. Of dimension 4. And now pick a complex symplectic form on C2 and just remove the imaginary part to get a real symplectic form. Now, this gives you an action of the 4-dimensional real symplectic group on R4, which is compatible with an action of the, so it has a subgroup, which is the 2-dimensional complex symplectic group, which is just SL2C, acting on CP1. And so usually when we think about circles and transformations which preserve circles, we'll only be looking at the Mobius transformations acting on CP1, and this is very reasonable. But there's this bigger group hiding behind, where if you insert this this additional piece of information where you keep track of the tangent of the normal directions, then you have this 10-dimensional group acting instead of the 6-dimensional SP2C, which is SL2C. Okay, so you get from this identification, you have a projection from RP3 down to CP1, right? This is just taking elements of C2 up to real multiple, so removing the origin. And this is taking elements here up to complex multiple. So it's a circle bundle. And in fact, it's isomorphic to the unit tangent bundle of CP1. Or if you want to think of it in a different way, this is like the hop vibration, but half of it. Right, if I did S3 instead of RP3, this would exactly be the hop vibration, and it's the same construction. So I'm thinking of RP3 as my unit tangent bundle of CP1, and the projection to CP1 is like forgetting the tangent direction. And all of this is how you formalize everything that I said before. So let me go back to this one. eraser. So when you take a Lagrangian subspace in R4 with this symplectic form, which is the real part of a complex symplectic form, they project the circles in CP1. Actually, any real subspace of this projects to a circle in CP1, but when you specify Lagrangians, you get this additional nice property that actually exactly two Lagrangians map to any given circles. So they project 2 to 1, unless they're also complex subspaces. Because remember, my R4 is secretly C2. So if my subspace is generated by a vector and I times that vector, then they project to a point. So one way, if your students ask you like, how do I visualize the Lagrangian Grassmannian in R4? That sounds like something impossible, but actually it's this Lie circle geometry space. So each Lagrangian in R4 can be bijectively identified with oriented circles or co-oriented circles, doesn't really matter, in S2, possibly of 0 radius, so this single points. So you allow these degenerate circles, and then you get a homogeneous space of SP4R, because SP4R clearly acts on this, and then it also acts on that. So your points are these circles together with a choice of either this orientation or that orientation. And to swap between one and the other, you multiply by I, which is why if you are a single point, you multiply by I, you are, if it stays the same, because points don't have an orientation, then it means it was a complex subspace to begin with. If you multiply by I, it doesn't do anything. So there wasn't a way to assign an orientation to begin with.
So the space of Lagrangians
Yes.
has this map to CP1.
Mm-hmm.
What is the space of the Lagrangians? I mean, maybe that's what you were saying before. It's hard to describe.
Oh, what is the definition of that?
No, I mean, I want to have a picture, like I want to identify it with a some sort of space which is mapping essentially 2 to 1 to a 2-sphere. But what is that space?
It does not map 2 to 1 to a 2-sphere.
Right. It projects to. Oh, so it goes to what? 2 to 1 to RP3.
No. So a Lagrangian is a subset of RP3. You can project it to RP3, you get a line. Because a Lagrangian in R4 is a 2-dimensional subspace. If you take a 2-dimensional subspace and look at it in projected space, it'll be a line. Right? Now, a line in real projected space, when you mod out by complex scalars using this projection, will give you a circle in CP1. That answers your question.
Yeah, I'm just trying to create an image in my mind of what's going on here. It's fine. Go ahead. I'll think about it.
Okay. So here on the Rosmanian of Lagrangian planes in R4, you have an action of SP4R. Which preserves all the structure given by the symplectic form and the linear structure given by the fact that it's a vector space and that we're looking at linear maps. On this side, this gives you these like tangency preserving transformations. And if I continue this dictionary between the symplectic geometry of R4 and the tangency geometry of circles, then my piecewise circular curves are not super complicated objects. So here I have started a dictionary where I have Lagrangians correspond to circles. The action of SP4 is a tangency preserving transformation. What else do I have? I have contact elements in RP3 or like unit tangent vectors in S2. Oh, this goes on that side. RP3 on this side has an action also of SP4R. And on this side, it corresponds to unit tangent vectors. And on this side, you have incidence, which is a point in RP3 is a line in R4. It can be part of a Lagrangian. It can lie inside the Lagrangian. So a point in RP3 can be a subset of a Lagrangian, which is an element of the space of all Lagrangians in R4. When you have this relation, it means that the unit tangent vector is normal to the circle, right? They're incident in the sense of Lie circle geometry. So, incidence here, which means you have a circle with an orientation and the unit tangent vector is part of that circle, right? So you can think of a subspace, it's a two-dimensional subspace, as a union of lines. It's a circle of lines, it's an RP1. And the way you move around in this circle of lines is by moving around the circle in the unit tangent bundle, like using this whole dictionary between RP3 and projecting to CP1 and identifying it with the unit tangent bundle. So then, what does it mean to have a piecewise circular curve? Or a circular polygon. That's also on this side. So a circular polygon on that side will correspond to a Legendrian polygon on that side. So what does that mean? Here I have my curve, which I don't know, is made out of arcs of circles with singularities possibly, and eventually it closes back up. On this side, all of the linear pieces, all of the circular pieces are linear because remember circles were Lagrangians in R4, which are linear. So I mean, these I can identify with certain lines in RP3, right? I call them Legendrian lines because that's because the symplectic structure on R4 induces a contact structure on RP3, and the projective lines which are tangent to the contact distribution are exactly those which come from Lagrangians in R4. So I can also call this Legendrian lines. So this is just a polygon in RP3 made out of pieces which are all Legendrian line segments. Or if you want, if you extend them, they come from a Lagrangian in R4, projected down to RP3. And so my classification problem from the beginning is just studying these objects up to SP4R. And the way you formalize everything is really by studying it on this side instead of that side. But on that side, you can draw pretty pictures. I should draw more, actually.
Yeah, so when you say Lagrangian in R4,
yes.
So is it a
Linear subspace.
but in the sense of vector space or
Yes, in the sense of vector spaces.
So they all pass by the origin.
Yes. Yes, two-dimensional subspace, two-dimensional Lagrangian vector subspace. Yeah. So how much? I guess I don't have much more time, right? 58. I don't know when I started. Maybe 5 minutes late or something. But essentially, I can give at least the idea of the proof of the theorem with the last 3 or 4 minutes. So I didn't have time to do the third section of the talk that I said at the beginning.
So did you? Okay, so you're looking at that space over there that I'm pointing at with the dimensions 4k minus 10.
Yes.
Did you say what the analog is in the Lagrangian picture?
I said what the points were, right? Yes, okay. So one circular polygon is a Legendrian polygon in R2.
So that you added all these qualifiers to it.
Right. What? Yes, that's true. So the generic will translate on that side also to a genericity condition, which means, for instance, that you never reuse the same Lagrangian twice. Like if I take how this extends to a Lagrangian subspace or to a full projective line, I never use another segment of that. So that will be one of the hypotheses. And the other one is that 2 vertices are never in the same Lagrangian unless they are adjacent vertices. Yeah. So they have pretty direct analogs to this side. Now, the way we prove that you have a special connected component is by defining a map from these Legendrian polygons, generic, with 2k vertices, to the set of pairwise transverse k tuples of isotropic flags. Oh yeah, that should have been part of the dictionary as well. So what is an isotropic flag? An isotropic flag is just a line in RP3 or a point in RP3 together with a Lagrangian containing it, or a line in R4 together with a Lagrangian containing it. So that's an isotropic flag. That's a Lagrangian, and this is a point in RP3. It's in it. And in the other piece of the dictionary, it's just a co-oriented circle together with a choice of point and vector, which is normal to the circle, right? So how do you take a Legendrian polygon with 2k vertices and define a k-tuple of isotropic flags? Well, you have like something like this. So, I mean, there's sort of different ways to map it, but if you choose like a vertex and call that the first vertex, then you have 2 choices of Lagrangians you can associate to that contain it, either this one or that one. Choose one. And because you want the flags to be transverse, you don't want to use that vertex because it's already taken by this line. So the next one will be this one. So that's maybe the first flag you associate. Then you associate this one. So you skip every other Lagrangian, and you define a k-tuple of flag from a polygon with two k vertices by going all the way around. Eventually, this polygon comes back. And then you just use a theorem of Fock-Goncharov, which is known about these spaces. There's a connected component that's very special in here. So this contains positive k-tuples of flags. As a connected component, and we know that it's homeomorphic to a ball. So you define a map like this. You characterize, like you show that it's a homeomorphism onto its image. I don't know what the whole image is actually, but I know that it contains this, and that it's a homeomorphism onto its image. So if I can give enough conditions here that characterize exactly the polygons which map to positive k-tuples of flags, then I know that what I characterized there is a connected component and it's homeomorphic to a ball. So I just essentially apply a theorem that already exists, which tells me this on this side is homeomorphic to a ball and is a connected component inside here. So even though I don't know exactly what the full image of this is, I know what the image of simple and decreasing curvature polygons is. I didn't have time to define what decreasing curvature was. It is the Maslov index. So when you have three Lagrangians in R4, there's this invariant of triples of Lagrangian subspaces called the Maslov index. It could take three possible values, like +1, 0, and -1. And you say that the Lagrangian polygon is decreasing curvature if the Maslov index is always +1 whenever it's defined. So it's not defined if the Lagrangians intersect. So you take every other one, and that should be always Maslov index +1. I should have prepared a shorter talk, but thank you for coming. Thank you for listening.
Are there any questions either from in the room or?
Well, where are you going from here?
Yeah, that's a very good question. So I want to, so the picture that's known is the SL3R picture. So in SL3R, we know what these positive tuples of flags are very well, and they correspond sort of to convex polygons in the projective plane. Those are very well understood, and you can use the geometry of convex polygons sort of as an intuition, but also to figure out things about these things called positive representations in SL3R, which is like the lowest possible, the easiest higher Teichmüller space to look at. When you know Teichmüller theory of like the geometry of hyperbolic surfaces, you look at representations of surface groups in SL3R, there's an analog there, and it has very strong geometric ties to the geometry of convex polygons. And now in the projective plane. Now this SP4R thing with these simple decreasing curvature polygons should be the right analog for SP4R. So if you want to study Hitchin representations into SP4R, you should study them using these curves, at least if you want to draw pictures in 2 dimensions, which I like to do. And then basically I'm trying to use as much of the like really powerful theory on this side to figure out like what's the interpretation in terms of circular polygons, because those are fun to play with.
So I had a question. Does simple have a nice characterization? I'm imagining something about rotation numbers or something.
Yeah, it's pretty easy. Well, so for these Legendrian polygons, one way to to represent them concretely, you can't, so it's a bit subtle. You cannot just fix the 2K vertices in the projective space, because then you don't know which segment to connect them with. So if you pick 2 points in projective space, you can either connect them directly or through infinity and back, right? But if you choose specific representatives for the projective equivalence classes, say like vectors in R4, concrete vectors, then it makes sense to connect them with a line segment, like take positive multiples of both of these vectors that will give you a choice of segment. And if you flip the sign of one of them, then it chooses the opposite segment. So to fix one of these, you fix 2K non-zero vectors in R4. 2K non-zero vectors in R4 will give you one of these polygons. And then you look at the symplectic product. You have this omega r between the vertices. So it will be 0 between adjacent vertices, because I said that edges should be Lagrangians. But then if they're not adjacent, it should always have the same sign. If this has a consistent sign, then it means that it's simple. But if it flips sign, then it's not simple. That's not satisfying as an answer. I don't know.
You seem really satisfying. I'm just trying to imagine how that manifests itself in your diagrams.
Oh, yeah, I don't.
Personally, whenever you say Lagrangians and symplectic, my brain starts wandering off. So I was just imagining if there was a nice.
Well, I mean, in here, simple just meant no self-intersections, right? So that's an easy picture.
Yeah, no, but I meant in sort of terms of your circle segments.
Yeah.
What does this mean? Is there some condition, like where I can go look at counts? You know,
I'll just look at one of them and know if it's simple without having to look at the whole.
Exactly.
Yeah, I don't know.
Okay.
Yes.
Yeah, so coming back to this equivalence at the beginning.
Yes.
So with this unit vector. So if you try to do this on the sphere with the standard round metric,
Yes.
then I guess you still deform to the same class of curve, but is it the same equivalence relation?
Yes.
And if you do it in a affine chart?
Yes.
Okay.
Maybe I should have described it that way to begin with.
Okay. It may just be that the speed is not the same, but the deformation is the same.
Yeah. So the one that I described using the Euclidean metric on a chart fixes, for instance, the point that's infinity. You can also think of it as a circle of radius 0. That one doesn't move because it doesn't have a well-defined radius. You don't translate it anywhere. But if you do the transformation that you're suggesting on the sphere, then all the points blow up, like they become circles, right? So there are no fixed points for yours, but they are all in the same class of transformations. They're all SP4R elements in the end.
Well, if there are no other questions, let's speaker again.